So when it comes to interpreting the results of the generalized linear mixed models, then the things to watch for are the fixed effects terms, and in particular the t-statistics corresponding to these fixed effects terms. So here we've got the table of t-statistics, and exactly as we've done before, the thing to look at here, where all the action and interesting bits are the second row downwards, and we want to see if any of these terms are significant, and the last column, which is actually underneath the regional label, gives you the p-value. So for instance, for the London Essex region, the p-value is 0.0003. For the North East Yorkshire region, the p-value is 0.8559. And if we go through, only the p-value for the London Essex region is significant. So what this means for the data example here is that this is noteworthy because we're getting the same regional effect identified using a different method. So if we look at the London Essex region term, this is significant and negative, so this indicates that respondents from this region are less likely to award a high score on these surveys. Okay, and just to sort of recap, this is significant because it matches the earlier regional effect that we identified. So in terms of the interpretation then, we retain previous evidence of a London effect precisely because the p-value on the previous slide should be 0.0003 there, beg your pardon, but it's in any case less than 0.05, which is the main thing to look for on this module. So you write this down in the Queen's English the opposite way around to how you work it out. So the coefficient of London is negative and statistically significant. So this suggests that London respondents are less likely to award high marks. We've got no evidence for any other regional effects, precisely because if you look back on the previous slide, the p-value for all the other regional terms is bigger than 0.05. Equivalently, the t-ratios for all the other regional terms are less than 2. And then one thing to watch for in this practical example is that it's noteworthy that you've got two different models telling you the same thing. So both linear mixed models and generalized linear mixed models point to the same London effect. And again, this is important because what you've got here then is two independent pieces of information telling you the same thing. And in this case, again, similar models should serve as a cross-check of each other. So two different approaches both identify then this London effect that people in this region tend to give lower marks. Less important this year because there's no final written exam, but I just wanted to give you some extra examples of numerical calculations that go alongside these outputs and an extra example of the sorts of checks that you might wish to do. So if you look at the fixed effects terms on slide 6.5 and you want to calculate, say, the probability that a London respondent gives a high score, so this is very similar to the logistic regression models we saw previously. So set log of the probability over 1 minus probability equal to the regression equation, and then this is the regression equation on slide 6.5 corresponding to the fixed effects terms. P over 1 minus P is equal to the exponential of the regression bit, and then the probability is calculated as the exponential of the regression bit over 1 plus this, so it comes out to be 0.702 in this case. So same sorts of numerical calculations that we've seen before, and I just wanted to here to give you an example of the sorts of things you might do to sort of check that everything is making sense and is as it should be. So what we're going to do on the next slide is calculate the probability that a Scotland respondent gives a high score, and what you should see is a higher value here, something that is of the same order of magnitude. So a numerical example then, calculate the probability that a Scotland respondent gives a high score. So if you look at slide 6.5 where these fixed effects terms are hiding, so set the log of the probability over 1 minus probability equal to the regression equation, and this regression equation is the fixed effects term, slide 6.5. So P over 1 minus P is equal to the exponential of the regression term, and then the probability is equal to the exponential of the regression term over 1 plus this, and it comes out in this case 0.761. So the idea here is that there's a sort of extra practice at these sorts of mechanical calculations, so it's not so important this year because you're not going to sit a written exam, but the important thing here is that this does give you a sanity check. Okay, so this calculated probability is higher for Scotland than for London, and again this matches the previous suggestion that the coefficient for London was negative and statistically significant, so the value is lower for London than it is for Scotland. But I think the other thing to sort of watch for here is not just that the answer is lower for London, but that these two numbers are of a comparable order of magnitude. So both those two things then, simple observations, but they give you an indication that you're on the right lines and you haven't made an obvious mistake. So the second part of this problem then is to test for regional effects in terms of the probability of giving a low score. So again, we've got a more complicated generalized linear mixed model going on here, but it's the same basic rhyme, rhythm and reason as regards the R commands that you've seen before. So R is like a robot, simultaneously very clever, very stupid, and again we're going to use these sets of two steps in the calculation here. So first of all, I want to compute the model. Secondly, show the results using the command summary. And as you see there, I do actually know how to spell the word summary. So the first command then, I just wanted to sort of try and explain what the R syntax is doing. So call the thing something sensible. Here I've gone for low 2. Didn't want to repeat the names that I'd used previously. This is going to be a generalized linear mixed model fitted by penalized quasi likelihood, and this is going to relate low to the region. The random term just means that there's some correlation in the data caused by repeat observations from the same hotel, and the family equals binomial bit again just means that what we've got here is a probability regression model, and R needs to know this. Okay, otherwise R will think it's a linear regression model and do the thing wrongly. So again, what we're looking for here is the fixed effects terms, and we want these t statistics corresponding to the fixed effects terms, and what we're looking for here is the p-value right at the end of the column. Hasn't displayed very neatly here in terms of the R output. So for instance, for some of the regions the p-value is below the label. So for the North East Yorkshire region the p-value is 0.7176. For the Northwest region the p-value is 0.7180, but how the output is produced by R, the p-value is in the very last column of the row, and we're just wanting to know here for which regions is this p-value less than 0.05. Well, again, the only region that has a significant effect is the London-Essex region. So how you would work this out, so the p-value is significant precisely because the p-value of 0.0274 is less than 0.05, and then in this case the coefficient is positive. So this means that in the London-Essex region respondents are more likely to give a low score compared to other regions. And then the estimated signs of the coefficients doesn't matter in other cases, precisely because in the other cases the p-values are bigger than 0.05. So similar interpretation then. So retain previous evidence of a London effect, p equals 0.0274, precisely because this p-value is less than 0.05, and then written down in the Queen's English, you write this down the opposite way to how you work it out. The coefficient of London is positive and statistically significant. This suggests that London respondents are more likely to award low marks. We've got no evidence of any other regional effects, so for all the other regions the p-value is bigger than 0.05, and alongside that the t-values are less than 2. And then because this is a practical data example, I think it's important here to emphasize that what you've got is that you've got similar models serving as a cross-check of each other, and two different approaches all giving you the same answer. Okay, both from the linear mixed effects models and from the generalized linear mixed effects models. So as it says on the bottom of the slide, 3 linear mixed and generalized linear mixed models now all point to the same London effect. So this is 1 linear mixed model in section 5 and 2 generalized linear mixed models in section 6 now all point to the same London effect. Respondents from this region generally giving lower scores on these online customer satisfaction surveys. And I just wanted to give another numerical example just to sort of show how this all ties together. Less important this year because you won't be sitting a final written exam. Okay, it's still important though in terms of just getting to grips with the thing, and just to re-emphasize again that the probability calculation comes from the fixed effects term that are listed on slide 6.10. So in order to do the calculation then, so set the log of the probability over 1 minus the probability equals to the regression equation, then take the exponential of both sides, so that p over 1 minus p equals the exponential of the regression term, and then p is equal to the exponential of the regression term over 1 plus this, and you get 0.044 in this case. Now I'm going to give another example in a moment for the Scotland region, and what you'd expect to find in this case, okay, is that you get something that's of a roughly similar order of magnitude, but it should be lower than this value here, precisely because, as we've just discussed on the previous slide, the coefficient for the London term was both positive and statistically significant. So for the second numerical example then, so how this works again is setting the log of the probability over 1 minus the probability equal to the regression equation, which in this case is the fixed effects term, and these are listed on slide 6.10. Then take the exponential of both sides, so p over 1 minus p equals the exponential of the regression term, and then p, the probability, would be the exponential of the regression term over 1 plus this, and you get, in this case, 0.028. So, as promised then, this serves as an important sanity check. So this calculated probability is both lower for Scotland than for London, which matches the previous observation that the coefficient for London was both positive and statistically significant. Also here, these two numbers are the same order of magnitude. Okay, so if they were markedly different, then this could be an indication that you'd made a mistake somewhere, but because this is similar but demonstrably less, this matches both the sort of general common sense thing that you get roughly similar answers for different regions, but that the answer should be lower for Scotland precisely because this regression term was positive and significant for the London region. Final cross-check then. Recall we've got 3 categories, so we only need 2 regression equations to describe the system. So just as a sort of common sense thing, as a final extra surety check, we could fit a generalized linear mixed model to estimate the probability of a medium score. So technically this should be a redundant step, precisely because you need only 2 regression equations to describe a system with 3 categories. But it's still useful to check this. So if we've done everything correctly and we've understood, what is going on in terms of the underlying maths, we would expect that when we fit this third model, we shouldn't identify any new regional effects. So if we fit this model and we do find a regional effect, then there's some indication that something is going wrong somewhere. Okay, but this shouldn't be the case. If we do fit this model, we should indeed find that there is no new regional effects that we identify at this stage. Okay, and I think similar to other areas of accounting and finance, what we're doing here is just to try and check the thing as much as possible and hopefully you can sort of see this as a natural thing to do, precisely because this is a practical problem that does arise from a genuine industrial problem in the electricity and water industry.